Hi everyone, this is Professor Oaks, and I know that all of us are going through some difficult times right now, and it might be a little bit hard to work from home or from the library or wherever you might be watching this from, but just know that everything will be okay, and I will definitely see you soon again in person. So, right now, I would like to just go over the notes as usual, as closely as we can. And this is section 2.7, combining functions. So when we talk about combining functions, we're talking about sums, which are adding, differences, which are subtracting, products, which are multiplying, and quotients, which are dividing. So this is the notation for adding functions. F plus g of x equals f of x plus g of x. F minus g of x equals f of x minus g of x. And f times g of x equals f of x times g of x. And f divided by g of x equals f of x divided by g of x. So you can see the domains over here. This one actually is a rational function, and we talked about those before. And in rational functions, you know that the denominator cannot be equal to 0, so any values where the denominator is equal to 0 are excluded from the domain. So let's do an example here. So we have given functions f of x equals 2x plus 1, and so I'll write that over here, 2x plus 1. And g of x equals x minus 3. I'll write that over here, x minus 3. Find each of the following and its domain. So f plus g of x equals f of x plus g of x. So that means just to add these together, 2x plus 1 plus x minus 3. Excuse me. So then we'll add these together just like usual. So we'll combine the like terms. X plus 2x, or 2x plus x, is 3x. And 1 minus 3 is a negative 2. So we end up with 3x minus 2. All right, now, again, since I am doing this by video, there may not be is best of a time for me to just stop and say, are there any questions or things like that? But always, please feel free to email me or contact me if you have any questions. So B, f plus f of x. F is 2x plus 1, f 2x plus 1. So f plus f of x is f of x plus f of x. So that's 2x plus 1 plus 2x plus 1. Let's combine the like terms. 2x plus 2x, 4x plus 1 is plus 2. So we have 4x plus 2. Again, of course, some of you may have seen that this could be f of x plus f of x, and that's 2f of x, which is 2 times 2x plus 1. Then you could distribute the 2 here to get 4x plus 2. If you did it that way, that's okay. Again, you get the same answer. And we talked about that a lot in class, where there is always more than one way to get the same answer. So I really don't care how you get your answer, as long as you show the correct work and the correct steps to get there. All right, so C, f minus g of x. F is 2x plus 1. G is x minus 3. Now, if you haven't noticed, in all of these other problems, when I'm writing this out, I'll write f of x minus g of x, but this is 2x plus 1 minus x minus 3. And if you've noticed, in all of these, I have been putting parentheses around the functions once I have been substituting them in. And it didn't matter in the first two as much, because I had addition, and I can add in in any order. But here I have subtraction, so I want to make sure to distribute, and I know that some of you always forget to do that, so please try not to distribute incorrectly or not at all. And so if I distribute, I have 2x plus 1 minus x plus 3. Combine like terms, 2x minus x is x, and plus 1 plus 3 is plus 4, and I'm left with x plus 4. All right, for D, g minus f of x, g is x minus 3, f is 2x plus 1, so this is g of x minus f of x. I'll write these in parentheses, x minus 3 minus 2x plus 1. Remember to distribute, just like in problem C, so I have x minus 3 minus 2x minus 1. And if I combine like terms, x minus 2x is negative x, negative 3 minus 1 is negative 4, so I end up with negative x minus 4. All right, so let's continue on page, the next page here. So, by the way, I probably will not actually leave that up on the screen because I know since this is a recording, you can go back and rewind or whatever, or replay whatever parts that you might need. So, E. Now, what I am going to do, though, is on the top of this page, I'm going to write down what the functions are from the last page so that I don't actually forget. And these will change for every problem, but these are all parts of the same problem here. So for E, f minus f of x was 2x plus 1 and 2x plus 1. Now this is f of x minus f of x, but you could substitute in 2x plus 1 and 2x plus 1 and then distribute and subtract, but the fact of the matter is f of x minus f of x is actually just going to be 0. So this actually ends up just being a number 0. All right, so page 1, I think it's still the same page. So f times g of x, f of x times g of x. So I'm following the rules from the previous page in terms of the notation, and f was 2x plus 1, g was x minus 3. This is multiplying, so I'll distribute 2x times x, 2x squared, 2x times negative 3, negative 6x, 1 times x is x, 1 times negative 3, negative 3. I'll combine the like terms, and I'll end up with 2x squared minus 5x minus 3. All right. Now, for g times f of x. So this is just multiplying the functions in a different order. So g of x times f of x. And for g of x, we have x minus 3, and f of x, 2x plus 1, will distribute 2x squared plus x minus 6x minus 3. And you can see that these two middle terms here are just in a different order. So if we combine like terms, we still are left with 2x squared minus 5x minus 3. All right, how about the next one here, f times f of x. That's f of x times f of x. So f of x was 2x plus 1, so we have 2x plus 1 times 2x plus 1. We'll distribute just like in problems G and F. So we're left with 4x squared plus 2x plus 2x plus 1. Combine like terms to get 4x squared plus 4x plus 1. There we go. All right, let's continue on here. F divided by g of x, so f of x divided by g of x. Now this is 2x plus 1 over x minus 3. And that's all that we really need to do at this point. We will actually divide these using long division later on, but not right now. But you do, by the way, need to write down the domain. And I didn't mention this before, but this in part A was a polynomial. So the domain was negative infinity to infinity, are all real numbers. In part B, 4x plus 2, remember, is a polynomial. So the domain is all real numbers, negative infinity to infinity. X plus 4 is a polynomial. So the domain is negative infinity to infinity. Part D, negative x minus 4 is a polynomial. So the domain is negative infinity to infinity. And in E, this is, even though it's a constant function, it's still a function with a domain of negative infinity to infinity. Part F, we get a polynomial. So that's a domain of negative infinity to infinity. G, a polynomial. So that has a domain of negative infinity to infinity. H is a polynomial. So it has a domain of negative infinity to infinity. But in part I, we see that we have a rational function as the result here. So x minus 3, the denominator, cannot equal 0. So x cannot equal 3. All right, when we add the 3 here, so that means that in interval notation, the domain is negative infinity to 3 or 3 to infinity. So please try to make sure that you write the domains out correctly for these rational functions here. All right, so for J, G divided by f of x, it's g of x divided by f of x, which is x minus 3 over 2x plus 1. So just the reciprocal of what we had in part I. And then, again, this is a rational function. So the denominator, 2x plus 1, cannot equal 0. So I'll subtract the 1. So 2x cannot equal negative 1, or x cannot equal negative 1/2 when I divide by 2 here. So in interval notation, I have that the domain is negative infinity to negative 1/2, or negative 1/2 to infinity. All right, K. K is a little bit trickier. F divided by f of x, that's f of x divided by f of x. So this is 2x plus 1 divided by 2x plus 1. But you have to use some caution here because it equals 1 if the 2x plus 1, the denominator, does not equal 0. And so then otherwise, it's undefined if 2x plus 1 does equal 0. All right, so just remember that this function, right, just as a brief review, since we have talked about piecewise functions before, y equals 2x plus 1, or f of x equals 2x plus 1 is a line. So just remember that. But if I want to well, okay, so remember that. But this is actually what we're graphing over here. So it's equal 1 if remember, when I solved this equation over here, x could not equal negative a half. If x is not equal to negative a half, so here is negative a half, here is 1, and so it's the function is undefined here, so I'll just have an open circle here. That's all that this means here. So the domain in interval notation is negative infinity to negative a half, or negative a half to infinity. All right. Oh, so this actually is the graph of this. All right. So L, this is f of x plus h minus f of x all over h. I've mentioned before that this is called the difference quotient. So let's find this. Since f of x is 2x plus 1, f of x plus h will substitute in x plus h wherever x is. So f of x plus h will be 2 times x plus h. Notice how I'm putting x plus h in parentheses plus 1 so that I will remember to distribute the 2 here. So I'm left with 2x plus 2h plus 1. So the difference quotient is 2x plus 2h plus 1 minus, again, I'm using parentheses, 2x plus 1 all over h. I'll distribute the negative symbol here to get 2x plus 2h plus 1 minus 2x minus 1 all over h. And then when the 2x is 0 out and the 1 0 out, I have 2h over h, and the h's divide out, and I'm left with 2. So again, this is 2 as long as this h here is not 0, because if h was 0, then that would mean that I would be dividing by 0, and that's not good. Okay, so hopefully that's okay here. So let's do example 2 here. Let f of x equals the square root of x squared minus 1, and g of x equals x over x plus 1. So find each of the following. So f is the square root of x squared minus 1. G is x over x plus 1. So this will be the square root of x squared minus 1 plus x over x plus 1. If you want to find a common denominator, you can, and that would just be writing this over 1 and multiplying by x plus 1. So we're left with square root of x squared minus 1 times x plus 1 plus x over x plus 1. Again, a common denominator isn't necessarily going to help much in this type of problem here. The one thing that I do want you to notice is that you cannot take the square root of each of the terms under the square root individually, so this square root needs to be left in the form that it is. In other words, what I'm saying is that the square root of x squared minus 1 does not equal x minus 1. All right, so do not make that mistake there. All right, so again, just do not make this mistake. All right, that would be really, really bad, and my cat will die if you make that mistake. All right, so find each of the following. F minus g, so square root of x squared minus 1 minus x over x plus 1. Again, I could find the common denominator if I wanted to, and that would be square root of x squared minus 1 times x plus 1 minus x all over x plus 1. All right, now let's find the domain of each of these. So the domain of f plus g, remember, under the square root, x squared minus 1, the x squared minus 1 must be greater than or equal to 0, since we can't take the square root of a negative number. And then remember how you solve these. It's factoring x plus 1, x minus 1 greater than or equal to 0. And then we find the zeros, which are negative 1 and 1. And because this x squared minus 1 has a y-intercept of negative 1, I can go ahead and draw the parabola here, and I can see the intervals right away where this is greater than or equal to 0, from negative infinity to negative 1, or 1 to infinity. However, I know that x over x plus 1 is a rational function, and the denominator x plus 1 cannot equal to 0. So if I subtract the 1, I get x cannot equal to negative 1. So that means that this right here, all right, since x cannot equal negative 1, needs to be changed to a parenthesis. So the domain is negative infinity to negative 1 with a parenthesis or bracket 1 to infinity. All right, so that one was a little bit tricky because of the square root and the rational function here. Now the same thing for the domain of f minus g. It really is that you have to be careful of the square root and the rational function being combined in the same problem. So these two actually have the same domain. Now f plus g of 4. All right, so f plus g of 4. So we know f plus g of x was square root of x squared minus 1 times x plus 1 plus x all over x plus 1. If I substitute in the 4 to get f plus g of 4, I have square root of 4 squared minus 1 times 4 plus 1 plus 4 all over 4 plus 1. So that's square root of 15 times 5. So 5 square root of 15 plus 4 over 5. Same thing for f minus g of x. We'll write that function down first. So we have square root of x squared minus 1 times x plus 1 minus x all over x plus 1. So f minus g of 4 will be square root of 4 squared minus 1 times 4 plus 1 minus 4 all over 4 plus 1. So that will be square root of 4 squared minus 1, that's square root of 15. 4 plus 1 is 5, so 5 square root of 15 minus 4 all over 5. So these are the values of f plus g of 4 and f minus g of 4. Now, let's move on to part C. Find each of the following. F times g of x. So f times g of x. Now I'm going to write these at the top of the page. F of x is square root of x squared minus 1. And g of x is x over x plus 1. Again, just so that I don't forget these. And f times g will be square root of x squared minus 1 times x over x plus 1. Again, I can write this in a simpler or nicer format, maybe of x square root of x squared minus 1 all over x plus 1. I would normally write the x first so that I don't accidentally multiply it to what's under the square root. Called the radicand there. So f divided by g, that will be square root of x squared minus 1 divided by x over x plus 1. Now remember that I can rewrite this by multiplying by the reciprocal. X squared minus 1 under the square root times x plus 1 over x. Or again, I can rewrite it with the part of x plus 1 in front of the square root so that I don't accidentally multiply it with what's under the square root. All right, here is the tricky part for these. Now the domain of f times g of x. I know originally, if you recall here, the part under the square root, x squared minus 1 had to be greater than or equal to 0, and the x plus 1 cannot equal 0, so that gives us the same domain as in these two parts that we had on the previous page. So domain is negative infinity to negative 1 or 1 to infinity. Now, here, f divided by g, we have a couple of things to watch out for. The numerator, this part, still cannot have what's under the square root be negative. So x squared minus 1 still has to be greater than or equal to 0. And then the denominator, x over x plus 1, has to not equal 0. And again, that the denominator of this cannot equal 0. All right, so remember that again, we have x cannot equal 0 because it would make the denominator here equal to 0, and x plus 1 cannot equal 0 because it will make the denominator of the denominator equal to 0. So x cannot equal to negative 1. So if I know that this x squared minus 1 greater than or equal to 0 has a solution of negative infinity to negative 1, or or 1 to infinity. I just want to make sure that I copied this down right from the last page there. Then, and again, you can always rewind or whatever you need to do to remember how I got that to be the domain of just the part that was under the square root here. So I know that x equals 0 was actually not even in this interval over here to begin with. So I actually know that the domain then is exactly the same as the other parts of the problem that we've done so far. So now let's find f times g of 4. So this will be, remember, f times g of x was x square root of x squared minus 1 over x plus 1. So f times g of 4 will be 4 times the square root of 4 squared minus 1 over 4 plus 1. So that will be 4 square root of 15 over 5. Good enough for me. All right, now for f divided by g of 4, remember f divided by g of x will be x plus 1 square root of x squared minus 1 over x. And that will give us, if we want f divided by g of 4, 4 plus 1 square root of 4 squared minus 1 all over 4. And if I simplify this again, this is not meant to be discouraging or anything, but again, I think that you definitely can do the arithmetic here, and it's 5 square root of 15 over 4. What a time to be alive. All right, so now let's move on to the next example, graphical addition. So this is just a way to add functions by looking at the graph. So if I look at a graph here, let's say at negative 3, I see that there's a point at negative 3, 0. That's fine. All right. Now here I have points at negative 2, 1, and at, well, you can sort of see that it's negative 2, negative about 0.75. So if I add the y values, 1 minus 0.75, I get about 0.25. Okay, so remember how this goes here. Now here is a point at oh boy, where is that? -1 and about 2.25, and about at -1 and a little bit below -1, but about -1, so 2.25 minus 1 is about 1.25. And then, let's see, there is a point about 0, 2, and now again, this is a little bit lower than -1, but they're very close. So I'm going to call this 0, -1, and 2 minus 1 is about, well, 2 minus 1 is 1. And then we have points at 1 and about, well, this is a little bit higher than the 2.25, but maybe not all the way to 2.5, so still about 2.25 or 2.3 or so. And this looks to be a point at about 1, -1/2. So 2.25 minus 1/2 is about 1.75 or so. So right about here. And then we have a point at about 2 and 3, and at 2, 0. So 3 minus 0 is still 3, and a point at let's see, well, 3, about 3, 1, and at 3, 2, and if I subtract the y values again, 2 minus 1 is 1, and then it has a point over here at 4, 0, but we're just going to subtract the y values for the points where the functions are both defined, and then connect the points about approximately as close as we can. All right, so I can see the pattern here. It goes sort of up and then back down. All right, so over here again, the g function was defined, but f was not, so we don't have to worry about this, and because it's outside of the domain of where both of the functions were defined. And here f was defined but g was not, so we don't have to worry about this because it's out of the domain of where both of the functions were defined again at the same time. All right, now I won't normally ask you to do graphical addition. That was just something fun for us to do. I don't know. I thought it was enjoyable. So composition of functions, or composite functions. So this is f of g of x. And remember that this is a f of g of x. So this is actually not multiplication. So remember, for multiplication, you saw me write the multiplication dot. So that was f of g times g of x. This means to substitute g of x into f of x. All right, so we've seen these two functions before in example 4. Given functions f of x equals 2x plus 1 and g of x is x minus 3, find each of the following and its domain. So f of g of x is f of g of x, and that means, again, to substitute g of x into f of x. So we have f of x minus 3, and then remember this was f of x, and we're going to substitute the x minus 3 everywhere there was an x in f of x, and that means including putting the g in parentheses so that we don't forget to distribute. So that will be 2 times x minus 3 plus 1. Distribute to get 2x minus 6 plus 1. Combine like terms to get 2x minus 5. All right. What a time to be alive. Now, g of f of x. This is g of f of x, like this. And I'll substitute now, this time, the f of x into g of x to get g of 2x plus 1. And remember, g of x was x minus 3, so wherever there was an x in g of x, I'm going to substitute 2x plus 1, which was f of x. So I have 2x plus 1 minus 3. Notice how I used parentheses, even though it wasn't necessarily necessary here. I did it anyway. And now I can just remove the parentheses. Since there's nothing to distribute, combine like terms, 2x minus 2. All right, so in this next example, here we go. The functions have changed, but it's a similar setup. Now, here we have numbers here, so that instead of just f of g of x, we have f of g of 2, which means that we don't necessarily have to find f of g of x first. We can just find f of g of 2. So if I do this, this means I can substitute the 2 into the g of x first. All right, and if I do that, I have 2 squared minus 2 times 2. So 2 squared is 4 minus 2 times 2, which is 4. So this is f of 0. And if I substitute 0 into f of x, I have 2 times 0 plus 3, which is 0 plus 3, which is 3. Oh, by the way, I did not find the domains on the last 2 of these problems, but remember, these are both polynomials, so the domain for both of these is negative infinity to infinity. So I apologize for that, but I tend to forget to write that down if I know that this is a polynomial where the function will be defined everywhere. All right, so now we have g of f of 2. So g of f of 2, that means to substitute the 2 in for the x in f of x. So we have g of 2 times 2 plus 3, which is 4, plus 3, which is 7. And g of 7 is 7 squared minus 2 times 7, or 49 minus 14, which is 35. All right, hopefully you are doing okay and there isn't too much confusion here. So f of negative 3. So f of negative 3. So we'll substitute the negative 3 into f to get f of 2 times negative 3 plus 3. So it's f of negative 6 plus 3. Negative 6 plus 3 is negative 3. And then we see that we end up with the same number that we just got. So we'll do that again. 2 times negative 3 plus 3, negative 6 plus 3, negative 3. That won't always happen, but in this case it did. All right, g of negative 1, rewrite that g of negative 1 like this. Substitute the negative 1 into g of x. Make sure to use parentheses extra carefully here because the x value we're substituting is negative. So negative 1 squared, remember, is negative 1 times negative 1, which is a positive 1. Negative 2 times negative 1 is a positive 2. 1 plus 2 is 3. And then g of 3 is 3 squared minus 2 times 3, or 9 minus 6, which is 3. All right, now for the next page here, find the domain of f of g of x if f of x is 2 over x minus 3 and g of x is 1 over x plus 4. So f of g of x is f of g of x like this. Now remember that what we have here is that we have f of 1 over x plus 4. So now the first thing that you can do is also substitute this into where the x is in f of x. So that's 2 over 1 over x plus 4 minus 3. Now, two things that you should notice is that, first of all, x plus 4 cannot equal 0 because it's in the denominator of the 1 over x plus 4. But this denominator also cannot equal 0. So 1 over x plus 4 minus 3 cannot equal 0. So one way to solve this is to add the 3. So 1 over x plus 4 cannot equal 3. And then I'll clear the fraction to get 1 cannot equal to 3 times x plus 4. Distribute to get 1 cannot equal to 3x plus 12. Subtract the 12 to get negative 11 cannot equal to 3x. And divide by 3 to get x cannot equal to negative 11 over 3. So I know if I subtract the 4 over here, x cannot equal negative 4, and x cannot equal negative 11 over 3. So now I can just write the domain in interval notation. So if I do that, domain in interval notation, let's see, what do I get? So negative infinity to negative 4, since x cannot equal negative 4, and then negative 4 to negative 11 over 3, since x cannot equal negative 11 over 3, and then a negative 11 over 3 to infinity. So this is the domain in interval notation. All right, here is another one here, domain of f of g of x if f of x equals 1 over x plus 2 and g of x is the square root of x plus 1. So f of g of x is f of g of x is square root of x plus 1. So if I substitute that in for x and f of x, I have 1 over the square root of x plus 1 plus 2. And I know two things here. And one of them is that's what's under the square root. X plus 1 has to be greater than or equal to 0. And the entire denominator, the square root of x plus 1 plus 2, cannot equal 0. All right, so if I subtract the 1, I have x can be greater than or equal to negative 1. But then if I subtract the 2 here, I have the square root of x plus 1 cannot equal negative 2. But since this had to be greater than or equal to negative 1 anyway, that means it could not equal negative 2. In other words, the domain in interval notation is negative 1 to infinity, but negative 2 was not in the domain anyway. All right, the domain of the square root of x plus 1. So this is the domain in interval notation. All right, let's try again here. Show that f of g of x equals g of f of x for, and actually this is really strange, it should be f of x like this because that actually looks like it's multiplying. Again, I mentioned that before, that you have to be careful about how these problems are set up and what they look like. So f of g of x is f of g of x, so we'll substitute the g of x into f of x, so we have f of x plus 5 over 3, which is 3 times x plus 5 over 3 plus, minus a 5. Divide out the 3's, so we have x plus 5 minus 5. 0 out the 5's, and we're left with x. So we did show that it was equal to x. Now we have g of f, that's g of f of x. Substitute the f into g, so we have 3x minus 5 plus 5 all over 3. 0 out the 5, so we have 3x over 3. Divide out the 3's, so we have x. So again, these were both equal to x. All right, find functions f and g such that f of g of x equals h of x. So that means really what we're saying is that the f of g of x, right? The f is the outer function and the g is the inner function. So we see that here x plus 5 is inside of the square root. So the outer function is square root of x and the inner function is x plus 5. So f of x is square root of x and g of x is it's just x plus 5. All right. Oh boy. So just sorry about that. So just so that you know, I was running to get this white out because I don't want you to think that I'm crazy here. If you look at this later and you're wondering where did the square root come from, it's just x plus 5. And if you want to be that picky, I can make that minus sign a little bit nicer for you too. All right. So you can always check this to make sure that it's what you expected. So if this is f of x and that's g of x, then we have f of x plus 5, but then when we substitute the x plus 5 into the square root, we get the square root of x plus 5, which is indeed h of x. All right, so this here is the solution. These are the two functions that you can write as f of g of x to give you the square root of x plus 5. All right, now I think that this is going to be the end of this section. I really am not very concerned actually about you doing the I'm really not concerned about you doing these two problems, but if you want to do these two problems, you can do them for fun on your own and in your backyard or in your basement or wherever you might be. You can do these two problems for fun on your own, but I am not going to do them right now. So that concludes this video lesson on combining functions. I hope that you truly did enjoy this video. All right, have a great day.